You're listening to the Science of Everything podcast, episode 89, The Atmosphere. I'm your host, James Fodor. In this episode, we're going to talk about Earth's atmosphere, particularly focusing on the composition. We'll look at the different atmospheric layers, and we'll also talk a bit about the Karman line, the ozone layer, and the ionosphere. So to give you a general overview of the Earth's atmosphere and some of its major properties. No specific recommended pre-listening for this episode, although this is part of a series of connected episodes which is leading up to talking about the science of climate change. So the previous two episodes, Cartography and Earth Seasons and Geography of Planet Earth, may be relevant. Also, a few points from episode 42, Gases and Gas Laws, may be pertinent as well. But mostly this is standalone. The atmosphere refers to the envelope of gases that surrounds the planet Earth. And the composition of Earth's atmosphere consists mostly of nitrogen, 78%. Now, that's contrary to what most people, I think, naively think, which is that oxygen is the main component of Earth's atmosphere. Oxygen is actually only the second largest component, 21%. This is by volume. And the third largest component is argon, which is an inert gas that doesn't really react with anything. It's a noble gas, so we don't hear about it very often. The fourth most common component by volume of the Earth's atmosphere is carbon dioxide, and it's been increasing in concentration in recent years, which we'll talk about when we get to discussing the science of climate change. Now, I should also say that these figures, 78% nitrogen, 21% oxygen, 1% argon, and trace other gases, are for dry air, because the atmosphere, varying at different levels of altitude in the atmosphere, but it contains significant portions of water vapor. So water vapor accounts for about 0.25% of the atmosphere by mass, and by volume it can comprise quite variable portions depending on temperature and altitude and region of the Earth's on the Earth's surface, depending on the climate and so on. So in cold and dry regions where there isn't going to be much water vapor in the air, it can be negligible, very little water vapor, up to about 5% by volume in hot, humid regions. So because of this variability, we typically give the composition of dry air rather than the actual composition, because that's going to vary too much depending on how much water vapor there is. So for dry air, 78% nitrogen, 21% oxygen, 1% argon, and then trace elements of other gases, the largest of which is carbon dioxide. There are also traces of neon, helium, methane, and other gases as well. Now, if all of Earth's atmosphere was uniformly distributed with a uniform density from sea level up, it would terminate abruptly at an altitude of about 8.5 kilometers above sea level. Of course, the atmosphere doesn't work like that. 8.5 kilometers, by the way, is just a little bit below Mount Everest. So if the atmosphere worked like that, Mount Everest would actually peak just a bit above the top of the top of the atmosphere. But of course, it doesn't work like that. In fact, the density of the gases in the atmosphere decreases exponentially with altitude. So it drops by a factor of half roughly every 5.6 kilometers. So that means the atmosphere keeps getting thinner and thinner as you go up, which also means that there's no real definition as to where the atmosphere ends. Theoretically, it just sort of keeps going, getting forever and ever sparser. So about half of the mass of the atmosphere lies below an altitude of 5.6 kilometers. So the other half is above that. About 90% is below 16 kilometers in height, and essentially all of it is below 100 kilometers in height. This is the so-called Karman line, which by convention marks the beginning of space. So usually it's understood that the atmosphere extends up to somewhere around 100 kilometers in height, and beyond that is space. But that's kind of arbitrary. There's some reason to choose that as a demarcation, as we'll talk about in a bit later. But also when studying the atmosphere from an Earth science perspective, we talk about it as extending beyond that as well, because there are gases above that altitude. It's just you have to pick some demarcation point for things like defining what space travel is, and 100 kilometers at around the Karman line is what is used for that purpose. Now, most of the atmosphere, and certainly all of the parts of the atmosphere that we regularly interact with, specifically the troposphere, stratosphere, and mesosphere, which we'll talk about in a minute, but those are the three lowermost layers. These are part of what's called the homosphere. These are regions of the atmosphere where the chemical composition is more or less constant, with altitude so that it doesn't vary depending on how high you go. This is important because some people have this idea that gases in the atmosphere will settle depending on their weight or density or something like that, but that's not true. That sort of thing only becomes an issue at the very highest levels of the atmosphere, which are part of what's called the heterosphere, where the composition does vary with altitude. But in the homosphere, the most parts we're familiar with, the atmosphere is sufficiently dense such that it behaves like an ideal gas, and that we talked about in the episode 42 on gases and gas laws. Effectively, in an ideal gas, really what matters is the density of particles and their temperature and the rate at which they collide with each other. Each particle, say whether it's a nitrogen molecule or an oxygen molecule, behaves in essentially the same way. And also there is sufficient density in an ideal gas so that they will mix together and the composition will be uniform throughout. So you don't have nitrogen bunching up in one part of the atmosphere and oxygen bunching up in the other part or something like that. There are a few exceptions like the ozone layer, which we'll talk about in a bit, but basically the parts of the atmosphere that we know and love, so to speak, troposphere, stratosphere, and the mesosphere, most familiar parts, the composition is fairly uniform. Okay, so now let's move to talk about the atmospheric layers, and we'll work from the outside in, so from generally the less to the more familiar layers of the atmosphere, and the sort of less to the more relevant from our perspective as human beings at least. The first thing to understand about atmospheric layers is that in general air pressure and density decrease with altitude. So I've sort of already alluded to this, but the basic idea is that air pressure is caused by the weight of the air above, that region. So the pressure is force divided by area. So pressure refers to sort of the force per unit area. But that force comes from the weight, so the gravitational attractive force essentially, of all of the air molecules sitting above a particular region on the Earth's surface. So as you move higher in altitude, as you move away from the surface of the Earth, there is less, in terms of total mass, less air molecules sitting over that particular region. And therefore the air pressure at that altitude decreases. And so as you move further and further up, there's less and less air pressure. Now that has consequences. For example, we need air pressure in order to be able to breathe and to extract oxygen from from the air we breathe. So if you climb up to Mount Everest, the air pressure is a lot lower at that high altitude, and it's therefore hard to breathe. And at the highest altitudes, there's not enough what's called partial pressure of oxygen. Effectively, that is the contribution of the total pressure by oxygen. There's not enough of that in order to get enough oxygen out of the air to breathe, and therefore if you're not going to die, you need artificial oxygen. So air pressure decreases with altitude, and density decreases with altitude as well. The reason density decreases with altitude is effectively the same reason as air pressure decreases, that the lower regions are compressed in less space by the force of the air sitting on top of them, whereas higher layers have less air sitting on top of them and therefore are not as compressed. Now, that, as I said before, that doesn't mean that the heavier gases sink to the bottom, because the Earth's atmosphere, at least at the lower layers, is well mixed and is sufficiently dense that there is a mixing of the gases, and you don't have this sort of sinking to the bottom. Temperature, however, is very different to air pressure and density. Air pressure and density pretty consistently decrease with altitude. Temperature, however, varies depending on the altitude. So in some regions of the atmosphere it decreases with altitude, in other regions it actually increases. And that might be very counterintuitive, because typically we think as you go high up in mountains or in aircraft, it gets very cold. And that's because pretty much all of the parts of the atmosphere that we are familiar with, like in aircraft, high mountains and so on, those are part of what's called the troposphere, which we'll talk about in a minute. But that's the lowest level of the atmosphere, and in the troposphere, temperature decreases with altitude. But in high levels of the atmosphere, that's not true. And so you can think of the temperature, if you were to plot, think of a graph with the altitude on the y-axis, so going higher up on the y-axis, and temperature on the x-axis. So effectively, I won't try and describe the exact shape, but it's a sort of a zigzaggy line. It goes back and forward. And what that means is that in some parts of the atmosphere, temperature decreases with altitude, and in some parts it increases, and in other parts it's fairly steady, so it's sort of a vertical line. And so according to the sort of kinks in this zigzag, so essentially when the line changes direction, and when instead of increasing with altitude it starts decreasing with altitude or stops changing much, at these kink points we can mark changes in boundaries. We can effectively classify regions according to where these kink points are. So that's how the classification of the layers of the atmosphere is generally done, by these temperature levels. There are other ways you can do it as well. The homosphere, heterosphere that I talked about before is by composition. That's a different way of breaking up the atmosphere, and there are other ways of doing it as well. But this method by temperature changes is I think a very useful one. And remember, the classification is not based on the level of the temperature, but it's based on whether the temperature is increasing with altitude or decreasing with altitude, primarily within this region. So that's important to bear in mind. That's what these levels are based on. This is called atmospheric stratification. There are 5 main layers here: the exosphere, the thermosphere, the mesosphere, the stratosphere, and the troposphere. That's going from out to in. And we'll talk about each of these in turn. So first we'll start with the exosphere. The exosphere extends from roughly 10,000 kilometers to 700-ish. Some sources say 500. It seems to vary exactly how they define it, but its innermost point is several hundred kilometers above the Earth's surface. Now, you'll notice that all of these distances are well above the Karman line, so in some sense they're considered to be part of space. So most people think of the atmosphere as part of the Earth and space as being beyond the atmosphere, but that sort of simple demarcation doesn't really work. The Earth's atmosphere continues into space. By 700 kilometers, if you were up there, it would look like you're in space. Now, to give you some comparison, you've probably seen some photos taken from the International Space Station, photos of the Earth, or photos sort of outwards, sideways, parallel to the Earth, to the Earth's orbit. So if you haven't, just look up those photos. Most people would say these are photos from space. We think of the space station as being in space. I mean, it's called the space station, right? We don't think of it as being in the Earth's atmosphere. However, the orbital altitude of the International Space Station is around 400 kilometers. Now, that means that it's actually it's not even in the exosphere, it's in the thermosphere, the next layer of the atmosphere. So not only is the International Space Station and all of the other pretty much all of the other satellites, some of them are much further out, but most of them are within the Earth's atmosphere, but they're not even in the furthest, in the outermost layer of the Earth's atmosphere. So the point is, if you were in the exosphere, it would look like you're in space. In fact, if you're in many parts of the thermosphere, it looks like you're in space. So for that reason, the exosphere is often sort of excluded from the atmosphere as being kind of beyond it. But in other sense, it's the outermost layer. Now, in the exosphere, the density of gas is extremely low. So the composition, this is not part of the homosphere, this is in the heterosphere. The composition is not the same with altitude. And its composition is quite different to the percentages I gave before. Those are mostly for the homosphere. Well, those are for the homosphere. The exosphere is composed mostly of very low density hydrogen and helium, with some other heavier molecules as well. The atoms are so far apart that they can travel hundreds of kilometers without colliding with each other. So it's an extremely diffuse gas. And because of this, it's far too far away from the Earth for any meteorological phenomena to be possible. So there's certainly no clouds or weather up there. However, the aurora borealis and aurora australis, those southern and northern lights that you see at very high latitudes, they sometimes occur in the lower parts of the exosphere, though they also overlap with the thermosphere, the next layer down. So there are phenomena that we can see that occur in the exosphere, and effectively the southern and northern lights occur because of charged particles that are traveling through the very highest regions of the Earth's atmosphere, the exosphere or the upper thermosphere. And so they're interacting with the other particles, the diffuse particles that are up there, and that gives off light. Apart from that, there's not too much to say about the exosphere. Let's then move on to the next layer down, which is the thermosphere. The thermosphere extends from roughly 80 kilometers up to, wherever you think the exosphere starts. Again, I've seen different figures from that, 500, 700 kilometers up. Now, the height of the thermosphere varies because of changes in solar activity, and that's true for most of the levels that I'm going to talk about. The exact demarcation point is not really possible to define because it varies depending on factors like weather and climate, latitude, solar activity, and so on. But it's going to be more or less the same, but there is variability. Now, the defining characteristic of the thermosphere that distinguishes it from the levels above and below is that its temperature gradually increases with altitude. So in other words, it gets hotter as you move up higher in the thermosphere. Now, that's a bit of a misleading way of saying it, because although temperature increases, it doesn't get hotter in a sense that we would recognize. The temperature in the thermosphere can actually get quite high. It can rise near the top parts up to as high as 1500 degrees Celsius, which sounds extremely hot. And you might wonder, how do our satellites, some of which are in this layer and some of which are higher, and say astronauts as they pass through this, how do they not melt? Well, the answer is that although the temperature is very high, the actual latent energy contained in the kinetic energy of the molecules in this layer is very low. That's because the gas molecules are so far apart that they don't interact very often, and the density is so low there just aren't very many of them. So at this point there's often several kilometers of average distance between molecules, so that is they'll travel a kilometer or two between collisions with the new air molecules. That's a lot less than in the exosphere, where it's hundreds of kilometers, but that's still a long way. The air is still very rarefied. Again, if you're in the thermosphere, it would still look like you were in space, a lot closer to the Earth than the exosphere, but it's still basically space. And therefore, although the temperature is high, the actual heat content is very low, so it wouldn't feel hot. It's just temperature is defined as average kinetic energy of the particles. So if their average kinetic energy is high, the temperature is high, even if there are hardly any particles to actually produce heat. If you're a bit confused about that, go back to the episode 42 on gases and gas laws, where I talk about that sort of thing in more detail. The reason, by the way, that the temperature is so high and is increasing with altitude here is in the thermosphere effectively is because of the very low density. That the particles at the very highest regions of the thermosphere have such low density that they just travel very fast and don't have much impeding their motion, whereas those further down have more impeding their motion. The density is higher, and therefore they're slowed down a bit, and therefore that's manifested in temperature. There's no water vapor in the thermosphere. There's not enough density to hold it there, and so there are no clouds in the thermosphere, and so no weather that we normally think of. But as noted before, the aurora sometimes occur in upper regions of the thermosphere. And as I also said, the International Space Station orbits in the thermosphere around 400 kilometers in altitude. Okay, so we've covered the two outermost layers, the exosphere and the thermosphere. Pretty diffuse, not really that much happening as far as sort of weather phenomena is concerned. Now we move into the homosphere, which is the bottom three layers, which are more interesting and more like what we would think of as the atmosphere. Now this is where the compositions that I talked about before, the nitrogen and oxygen, so forth, this is where those compositions more or less hold, and this is where some of the interesting weather stuff starts happening. So the middle layer of the atmosphere is called the mesosphere. That's the third layer in, and it extends roughly from 50 to 80 kilometers. So it's just below the thermosphere and just above the stratosphere. In the mesosphere, temperatures drop with increasing altitude, so that's sort of as we would expect. The top of the mesosphere is actually the coldest place on Earth. It has an average temperature of around minus 85 degrees Celsius. Extremely cold up there. Just below the mesopause, so the mesopause is the altitude at the top of the mesosphere, where temperatures then start to increase again because the densities get so low, the particle densities get so low. Just below the mesopause, the air is so cold that any water vapor there will sublimate and form what is called noctilucent clouds, which are very high altitude clouds that you can sometimes see if the light reflects on them near sunlight or sunset. The mesosphere is mostly accessed by rockets and rocket-powered aircraft. You'll also see meteors as they pass through the mesosphere and start to burn up when the atmosphere gets thick enough for that to happen. The mesosphere is middled in a number of ways. It's sort of where you would start to recognize an atmosphere as being. You're certainly not in space anymore. It's too low for, say, satellites to orbit in, or for the space station to be at that altitude. There's too much drag, but it's also too high for us to access with any aircraft, and therefore the only real way we can access it is through sounding rockets, essentially rockets on ballistic trajectories. They don't go into orbit, but they go up into very high altitudes. And as I said, there's no real weather phenomenon here, apart from the noctilucent clouds and meteors and a few other interesting phenomena. But most of what we think of as weather happens at lower altitudes than that. And as I mentioned, temperature decreases with altitude. That's important. Okay, now let's move on to the stratosphere. Probably you've heard of the stratosphere. For some reason, stratosphere seems to be a word that people know more than troposphere, although maybe that's just me. I don't know. Let me know if that's different to you. But stratosphere is actually not the lowest level of the atmosphere. Troposphere is. So stratosphere is the second lowest layer, which is just below the mesosphere. The stratosphere extends roughly from 10 to 50 kilometers up, or 12 to 50 kilometers up. It varies a bit again. In the stratosphere, the characteristic feature is that temperatures actually increase or are roughly constant or increase with altitude. Now, as I mentioned before, that's counterintuitive. We think of high altitudes as being cold. That's because commercial jets and all of the highest mountains are all located in the troposphere. That's the next layer down, the lowest level of the atmosphere. In the troposphere, temperature does decrease with altitude. So if you were to go up a bit higher than pretty much anything that we tend to experience into the stratosphere, temperatures actually begin to increase with altitude. Now, the big reason for this is because, crudely, of the ozone layer. The ozone layer exists in the stratosphere. I'll talk a bit more about the ozone layer later, but the basic idea is that in the stratosphere, there is a greater relative abundance of particular types of molecules that absorb ultraviolet radiation from the sun. And because of all of the energy that's being absorbed in these layers that aren't absorbed nearly as much in other layers, temperature increases with altitude here. So the stratosphere is, particularly the top, is much warmer than the top of the troposphere. The top of the stratosphere, which has the highest temperatures of the stratosphere, obviously because it's increasing over the course of the stratosphere, temperatures get to around 0 Celsius, which might not sound like a lot, but when you compare that to the top of the mesosphere, which is minus 85, and the top of the troposphere, which I think is like around minus 60, it's actually quite warm. Now, because of this increase in temperature with altitude, the stratosphere is quite different in terms of its meteorological conditions compared to the troposphere. One of the main drivers of weather conditions and also climatic conditions in the troposphere, the lowest level of the atmosphere, is convection cells of air. And I would have talked a bit about this, I think, in gases and gas laws, or possibly a different episode. But a convection cell is essentially a current of air or fluid, but in this case we're talking about air specifically, that transfers heat from hot regions to cold regions. And in the case of the troposphere, it is a method in which energy is moved from the surface of the Earth, where a lot of it is absorbed from the sun, so it gets hot. It transfers that energy through convection cells, essentially through the flow of hot air up away from the surface of the Earth to higher regions of the atmosphere, where it gradually gets colder. So these are convection cells. Now, convection cells are dependent on temperature gradients, so you're only going to get convection from one region to another if there's a temperature difference, specifically if you have hot to cold gradient, which does exist in the troposphere usually. However, it doesn't exist in the stratosphere precisely because of this increasing temperature with altitude. So basically, clouds and other phenomena that form weather in the troposphere generally don't exist. They don't continue up into the stratosphere because there's effectively a ceiling, a cap enforced by this temperature inversion. This can occur in the troposphere sometimes as well, which can lead to smog getting trapped over cities if there's a temperature inversion. But it happens on a grosser scale with the transition from the troposphere to the stratosphere. And so for this reason, the stratosphere is generally quite stable atmospherically. You don't have large cloud formation or air turbulences that you get in the troposphere because you can't get these same convection currents. In the troposphere, you've got really hot, dense air from the lower atmosphere, which then can convect upwards to the cooler temperatures of the upper troposphere, and therefore drive these big energy flows, which give rise to weather. But in the stratosphere, it's reversed. The hottest regions at the top of the stratosphere are also the least dense, and so you just can't have these same big convection cell energy flows. So that's why you have the big difference, and effectively why the stratosphere is quite distinctive from the troposphere below it and the mesosphere above it, both of which have decreasing temperature with altitude. There are some types of clouds, like polar stratospheric clouds, that can occasionally be seen in the lower parts of the stratosphere. And I think that occurs largely over polar regions where you just get the sublimation of the whatever residual air vapor is there. But for the most part, you don't see much weather phenomenon in the stratosphere. The stratosphere is mostly accessed by weather balloons and also by some types of jet aircraft, like particularly military aircraft. Commercial aircraft generally fly near the top of the troposphere. So aircraft can fly in the stratosphere, but they have to be specially designed to do so. And you need generally relatively advanced jet aircraft to be able to fly comfortably in the stratosphere. Propeller-driven aircraft are relegated to the troposphere, to which we now turn. Now, the troposphere is the lowest part of the Earth's atmosphere. It extends from sea level up to around 12 kilometers, although this altitude varies, as I mentioned before, by several kilometers. Actually varies by quite a bit. It's more like 9 kilometers at the poles and 17 kilometers at the equator. That's partly due to the bulging at the Earth's surface due to centrifugal effects of the Earth's rotation. And there's also variations due to weather. The troposphere is bounded at the top by the tropopause. That's where the temperature inversion occurs that I talked about. So that's when you have the decreasing temperature with altitude stop, and the temperature then begins, well, first it sort of levels out and then begins to increase with altitude. So there's a tropopause at the top of the troposphere where that happens. There's also a mesopause at the top of the mesosphere where that happens. So generally, temperature declines with increasing altitude in the troposphere due to the effects that I talk about. Energy transfer away from the surface of the Earth, where lots of energy is absorbed. As you get further away from that, the energy is diffused, and therefore the temperature gradually reduces with altitude. That is until, of course, you get to the tropopause and the stratosphere, where you get that UV absorption that changes things up. Again, because of the density and temperature profiles that I just talked about, this promotes vertical mixing in the troposphere, those big convection cells that I mentioned. This gives rise to most of our weather phenomenon, and also some climatic phenomena too, which we'll talk about in future episodes. The troposphere contains about 80% of the mass of the Earth's atmosphere, so I mean really most of the atmosphere is in the troposphere, and essentially all of its weather phenomenon. So when people talk about the atmosphere, implicitly they're talking mostly about the troposphere, although technically it's only the very lowest level of the atmosphere. Pretty much all of the clouds that you know and love, or maybe not love so much, I don't know, depending on your attitudes to such things, exist exclusively in the troposphere. The very tall cumulonimbus clouds can penetrate the tropopause sometimes and extend in the lower part of the stratosphere, and there are a few unusual types of clouds that can exist in the stratosphere, even the mesosphere. But for the most part, weather phenomena, clouds and everything's all in the troposphere, and pretty much all conventional aviation, aside for some military applications, occur in the troposphere as well. So that concludes our discussion of the layers of the atmosphere. Hopefully you have a bit of a better understanding about how those work in connection with each other. I'll just give a quick sort of recap of that so that you've got the picture. And this time we'll work in the opposite direction. We'll start at sea level and move upwards. So starting at sea level, we have the troposphere, which is the densest layer of the atmosphere, and extends up for roughly 10 kilometers, 10, 12 kilometers, depending on exactly what your latitude is. Remember, latitude is how close you are to the poles or equator. Altitude is how far away you are from ocean level. So in the troposphere, temperature decreases with altitude. Effectively, that's because the Earth's surface is heated by absorbing a lot of sunlight and then emitting that again. And as you move further away from that, or as the air moves further away from that, the energy is diffused, and therefore temperature decreases. So that's sort of the effect you would expect naively. That's what occurs in the troposphere. That's also what occurs in the mesosphere at the third layer. The stratosphere, roughly between 10 and 50 kilometers, let's say, that lies in between the troposphere and the mesosphere, is different. Temperature increases in the stratosphere. This is largely because of the ozone layer, higher concentrations of ozone, which is a particular compound that is good at absorbing ultraviolet radiation from the sun. Because of this extra heat that it absorbs, temperature actually increases with altitude here. Most of the weather occurs in the troposphere, a few weather phenomena in the stratosphere. Most aviation occurs in the troposphere, some aviation in the stratosphere. The mesosphere is beyond pretty much all weather and pretty much all flight. We can only access it through sounding rockets and some very high altitude weather balloons. The next layer of the altitude, the fourth region, is called the thermosphere. It extends roughly from 80, 90 or so up to 500, 600, 700 kilometers above the Earth's surface. If you were to be in the thermosphere, it would look like you're in space. Many satellites exist in the thermosphere, and the space station orbits here. Temperature increases with the thermosphere, largely owing to the fact that particles are so diffuse that the higher altitude ones are even more diffuse and therefore have more freedom to move about with high kinetic energies. But that doesn't really translate to hotness in the way we would understand it because the particles are so diffuse. But nevertheless, temperatures do increase with altitude in the thermosphere. Anything above this 500, 600, 700 line is called the exosphere, where some of the higher altitude satellites orbit, and effectively is indistinguishable from most some ordinary perspectives from space. The Karman line, which demarcates officially as far as such things go, the boundary of space, occurs in the lower thermosphere. So most certainly the exosphere is effectively space and gradually fades into the background space. There's no clean cutoff as to where the atmosphere really ends exactly. Okay, so that's a discussion of the stratification of the atmosphere and the main layers and their properties. Now I'll just talk about a few phenomena that I've mentioned, but I want to go into a bit more detail into the Karman line, the ozone layer, and the ionosphere. So the Karman line is, well, it's an imaginary line at altitude of about 100 kilometers that it conventionally marks out the boundary between the atmosphere, well, between space and not space, I suppose, although technically the atmosphere is on either side of it. So parts of the atmosphere are in space and parts of the atmosphere are not in space, I suppose. But this sort of arbitrary demarcation occurs at the Karman line of 100 kilometers. So if you go above that, you're an astronaut and you're considered to have been in space. Now, what's the significance of the Karman line? It's not just that someone thought that 100 kilometers sounded nice, although it kind of does. There's actually a reason for specifying this. And it's named after the guy who came up with it, obviously. Effectively, the Karman line marks out the outer limit to which aviation is even theoretically possible. I'm not aware of any aircraft that have got up to this level, this altitude before, but it is at least theoretically possible to build aircraft that are able to stay aloft using the force of lift up to the altitude of 100 kilometers. Above that, it's theoretically impossible. So the Karman line marks out the maximum possible altitude that you could have an aircraft that kept itself aloft through the force of lift. Above that, you can sort of stay aloft in a sense, but only by either being in a very high arc ballistic trajectory or by orbiting the Earth, not through the force of lift that keeps aircraft in the air. Now, I haven't really done an episode on how aircraft work. It's actually quite interesting, but for the simple perspective we need at the moment, the basic idea is that aircraft keep themselves aloft by traveling fast enough through the air so that they can generate sufficient lift force to keep them up. And that lift force occurs essentially by pushing air down. So aircraft travel forward. In doing so, they push air backwards as well, but they push some air downwards, which generates a lift force keeping them up. This is very highly simplified, but it's good enough for our purposes here. The faster they can travel forwards, the more air they can push down and the greater lift force they can generate. Now, lift force is affected, as I mentioned, by airspeed, speed relative to the air. However, it also depends on the density of the air. So the denser the air is, the easier it is to generate a lift force. That's the same phenomenon as the fact that it's easier to float in salty water than it is to float in fresh water, because the salt content increases the density of the water and helps you stay afloat. It's more or less the same idea. So that means lift decreases with altitude because the air density decreases with altitude. So it's harder to stay aloft at higher and higher altitudes. That's why aircraft design gets trickier. Well, was one reason why aircraft design gets trickier as you want the airplanes to reach higher and higher altitudes, because it's harder to generate that enough lift force to keep the weight of the plane aloft. So therefore, all other factors remaining equal, airspeed must increase to compensate for the lower air density as you get to higher and higher altitudes. At the point of the Karman line, an aircraft would have to be traveling at orbital velocity in order to generate enough lift force to keep itself aloft. Orbital velocity essentially is the velocity at which you are orbiting the Earth. Effectively, it's the rate at which the Earth's surface is curving away from you is the same as the rate at which you're falling down to the Earth's surface. I think I might have talked about this in episode 1, explaining gravity. So when an object is in orbit about the Earth, effectively what's happening is it's in free fall. Meaning it's constantly falling to the Earth's surface because of the force of gravity. The reason that it doesn't actually hit the Earth's surface is because basically an object in orbit is moving so fast relative to the surface of the Earth, parallel to the surface of the Earth. It's moving so fast in that direction that the rate at which the Earth curves away from it is the same as the rate at which the object falls towards the surface of the Earth. And so it's effectively it's constantly falling, but it never gets there. For more details, see the episode on gravity. But the point is, that's a very distinctive mechanism from generating lift to stay afloat like to stay aloft like an aircraft does. So the point is that if the velocity you have to be traveling at to generate enough lift to stay aloft is in fact orbital velocity, then you're not really flying anymore, you're orbiting. So the Karman line marks out the point where aeronautical flight becomes impossible essentially, and you become an orbiting object. So it's because of this obviously being a relevant distinction between aircraft and spacecraft, it seems a logical point to mark the boundary between sort of the atmosphere and space. The Karman line is not exactly at 100 kilometers. The exact point at which flight becomes impossible is a complicated function of exactly what the temperature and pressure of the gases and so on is, but it occurs at around 100 kilometers, so that's sort of defined as the altitude that's convenient. Okay, so that's the Karman line that I mentioned that demarcates the line where space begins, sort of by convention. Next, I'm going to talk about the ozone layer. The ozone layer, or ozone shield, is a region in the Earth's stratosphere that absorbs most of the sun's ultraviolet radiation. It contains high concentrations of ozone, which is 3 atoms of oxygen all bonded into one molecule. So remember, oxygen in the air is comprised of O2 molecules, 2 oxygen atoms in a molecule. Ozone is 3 oxygen atoms combined in a molecule. All of the atmosphere, or the lower regions at least, have some ozone in them, but the ozone layer in the stratosphere has much larger concentrations. It contains around 10 parts per million of ozone compared to about 0.3 parts per million of the rest of the Earth's atmosphere. So, something like 30 times the concentration of ozone. It's found the ozone layer is mostly in the lower portion of the stratosphere, about 20 to 30 kilometers above the surface of the Earth, although its thickness varies geographically and also seasonally, as we'll talk about in a moment. The ozone layer absorbs something like 98% of the sun's medium frequency ultraviolet light. So that's of wavelengths sort of just below the visible spectrum. These wavelengths of light would otherwise be very dangerous to exposed life forms on the surface, effectively because they have sufficiently high energies that they're able to disrupt proteins and nucleic acid and other biomolecules that we need to survive. That's why exposure to too much ultraviolet radiation can cause cancer, effectively, because of these disruptions to the bonds of the molecules. It's got the right energies to be able to do that. So ultraviolet radiation is harmful, and the fact that the ozone layer is able to absorb nearly all of it is very useful for our purposes, so that we can, survive on the surface of the Earth. Unfortunately for us, the ozone layer can be depleted by certain chemicals, particularly free radical catalysts. Now, a free radical is a type of molecule that has an unpaired electron. An unpaired electron meaning that electrons like to exist in atomic orbitals in pairs, one spin up and one spin down. Don't worry if you don't know exactly what that means. I've talked about it in previous episodes on this sort of thing, but the point is that they are in a lower energy state when the electrons are paired, and if there's one that's left by its lonesome, the molecule is in a higher energy state, and therefore it tends to be very reactive. So some of these types of molecules, nitric oxide, nitrous oxide, hydroxyl, chlorine, bromine, and some others are very reactive and will tend to react with ozone, converting it into its O2 form or other forms. Now, chlorofluorocarbons and also bromofluorocarbons are compounds that have significant concentrations of halogens in them, so particularly bromine and chlorine, which are reactive radicals. Chlorofluorocarbons and bromofluorocarbons are generally highly stable, so they can survive rising up high in the stratosphere. This differs from a lot of other compounds that will be broken down or react before they get up into the stratosphere. But these carbons, the CFCs and BFCs, can get up to the stratosphere level where the ozone is. There, they will survive for a long time, but eventually the chlorine and bromine radicals are liberated by the action of ultraviolet light. So effectively they break free, and then these radicals are free to initiate and catalyze a chain reaction of breaking down tens of thousands of ozone molecules. A catalyst, remember, is something that's not used up in the reaction. It's not changed. So the chlorine and bromine can react with molecules of ozone, convert them into, say, O2 molecules, and then themselves remain unchanged and then go into to break down further ozone molecules, and they can stay up in the atmosphere for a very long time. So these molecules, particularly the chlorofluorocarbons and bromofluorocarbons, when released into the atmosphere, can have devastating effects on the ozone layer. Reducing the concentration of ozone in the ozone layer reduces the absorption of ultraviolet radiation, and therefore creating what are called holes in the ozone layer, or at least a thinning of the ozone layer. It varies. The extent of the thinning or of holes varies seasonally by complicated effects. It also depends on the region of the Earth's surface. These holes were originally discovered, I think, in the late 1970s. It was first reported in 1985. Reductions of up to 70% of the mass of the ozone column were first observed in the southern hemisphere over Antarctica in 1985. So these can be very substantial reductions. The degree of the reduction varies from year to year, but up to 70% in the worst years is very substantial. Other years it's less, but it's still significant. So these compounds, chlorofluorocarbons, bromofluorocarbons, and others, are, I don't think I said, but predominantly man-made. So they're released into the atmosphere. They're stable, so they travel high up into the stratosphere where the ozone is, and then gradually radicals are released, which are able to catalyze many rounds of breaking down of ozone molecules. And this is what has caused these holes and also thinning of the ozone layer since roughly the late 1970s. Now, this is a big problem, as I mentioned, because ozone is important for keeping out ultraviolet radiation, and thinning and holes in the ozone layer have been attributed to some proportion, I don't know exactly how much, but some proportion of rises in skin cancer and other illnesses like that in particular regions of the world. The reason, by the way, that the holes in the ozone layer are most pronounced over the Arctic and the Antarctic, even though obviously hardly any pollutants are actually produced in those areas, so it's a bit counterintuitive at first, is effectively because the temperature matters a lot. So reactions typically take place most effectively in polar stratospheric clouds. I actually mentioned those previously, particularly cold clouds that occur in the stratosphere particularly over the Antarctic and the Arctic. The reactions occur most effectively there, and so that's where the ozone depletion is worst. The pollutants are not produced over the polar regions, but they're able to travel there because, as I mentioned before, the lower regions of the atmosphere mix very effectively. There's two aspects of ozone depletion. One is a gradual thinning of the average ozone layer of the whole of the Earth by about 4% since the late 70s. That has effects as well, because every bit of the diminution of the effectiveness of the ozone layer has an effect on, skin cancer and other conditions. So that's bad. But particularly bad are the whopping, 20, 30, 50, 70% reductions in the ozone column observed in the polar regions in some years. It varies from year to year and by the season. So it's quite variable. There aren't permanent holes in the ozone layer that exist over the Antarctic, but seasonally the holes open up and then sort of close to varying degrees. Thankfully, however, there has been relatively swift action since the original discovery of concerns about ozone depletion. So in 1987, the Montreal Protocol was signed, which phased out the production of many types of chlorofluorocarbons and bromofluorocarbons, which had a wide variety of industrial uses as refrigerants, solvents, fire retardants, and other things like that. But in most cases, alternatives were found. There were a few exceptions where exemptions were granted. But this was actually an international treaty that was ratified by essentially all countries and has been extremely successful in dramatically reducing the emissions of all of these ozone-depleting compounds, which are now well below the levels that they were in the 80s, and continuing to decrease. The hole in the ozone, or the holes in the ozone layer, have stabilized in the past roughly 10-ish years, I think, and ozone thickness is predicted to return to pre-1980s levels sometime around mid-century. So it's going to take a while to recover, recalling that the catalysts that are already up there in the atmosphere are still causing ozone depletion. It's just that we're no longer adding to them at the same rate. So gradually they'll be broken down over time, but that's going to take several decades. But the problem is not getting any worse, and it's gradually getting better. So there's good news on that front, unlike the global warming case, where action has been much more difficult to bring about. The final thing that I wanted to just briefly mention is the ionosphere. This is the ionized part of the Earth's upper atmosphere, which extends from about 60 kilometers up to 1,000 kilometers in altitude. So that includes the upper parts of the mesosphere and the thermosphere, and also parts of the exosphere. So the ionosphere is, well, it's ionized, as I mentioned. It's ionized by solar radiation. So remember, ionization is the process of becoming electrically charged. So the atoms in the particles in these regions lose some of their electrons, or potentially gain electrons, and therefore become electrically charged. So effectively, you can think of the ionosphere as a shell of electrons and charged atoms that surrounds the Earth at this high altitude, and exists as a result of ultraviolet radiation, which is able to ionize these molecules. Now, because ionization depends on the activity of the sun, the extent of ionization varies with the amount of radiation that's received. So it varies seasonally and with solar activity and other factors like that. Now, the interesting thing about the ionosphere is that because it effectively represents a layer of electrons around the Earth, a charged layer, and electrons, particularly sort of a free sea of electrons, react with electromagnetic radiation, just like, say, metals reflect light. It's effectively the same phenomenon. The ionosphere is actually able to reflect certain types of electromagnetic radiation. Now, we're not talking about the ultraviolet radiation that is absorbed to create the ionosphere in the first place. That's much higher energy, and that's not reflection anyway. That's absorption and ionizing the atom by freeing the electron. Here we're talking about a larger scale phenomenon where longer length wavelength is reflected as a result of its interaction with the charged sea of electrons. Again, it's effectively the same as what happens when light is reflected off the surface of a mirror, say, or other metals, which have that sea of electrons which is able to interact with the electromagnetic radiation and reflect light quite well. The wavelengths that are reflected by, or that can be reflected by the ionosphere, are certain bandwidths in the high frequency radio waves. And so the ionosphere is actually able to reflect these types of radio waves back toward the surface of the Earth, where they are able to actually bounce off the Earth and then back off the ionosphere and so on a number of times. So this actually enables people to communicate with shortwave radios even over the horizon of the Earth. So when they can't directly see each other, when you can't shoot waves directly from one observer from the emitter to the observer because the curve of the Earth is in the way, you can actually bounce them off the ionosphere, and they'll bounce back off the Earth and back off the ionosphere a couple of times and eventually reach their intended destination.
So this is called skipping or skywave propagation. It's been used since the 1920s to communicate internationally. The process is a bit tricky because there's some obviously loss at each stage of the bouncing. So often the signal quality is not so great, and that's going to depend on, the solar activity and how thick the ionosphere is, and atmospheric effects and a bunch of other things. So it's not really used much anymore because we have satellite communications and underwater internet cables and other things that are much more effective for sending signals generally. But it still can be done, and radio hobbyists still do it. It's a pretty cool phenomenon, though not something that you would initially expect to be possible, but it's a result of the ionosphere and the charged particles that exist up there as a result of UV radiation causing ionization. Okay, so that concludes what I wanted to discuss in this episode, the layers of the atmosphere and the ozone layer, Karman line, and the ionosphere. Hopefully that's given a bit of a richer picture of the atmosphere for you and a bit of a better understanding, which we'll then put to use in the next couple of episodes when we get around to talking about climates and weather effects. So, if you enjoyed this episode, please give the podcast a favorable review. Click on the aggregator of your choice. You can also like our Facebook page. If you just go to Facebook and type in the Science of Everything podcast, give our Facebook page a like. That also helps to promote the show. If you have any questions or suggestions for future episodes or any other feedback, you can send me an email. My address is fods12@gmail.com. That's FODS12@gmail.com. Thank you very much for listening, and I'll talk to you next time.